I'm going to demonstrate how to do the homework problems for Chapter 11 in BQM. In question 1, we're given a sample of 5 observations. So I'm going to copy this sample into Excel. Now notice that the numbers are all in one cell, A1. If you click on that cell A1 and you click on data, text to columns, delimited, next, and you then click comma, notice that when comma is not clicked, you don't have any columns here. But when you click on comma, wherever Excel sees a comma, it creates a new column. And then you can hit next and finish. Okay, so now the observations are in, each observation is in its own cell. I like to rotate the data, so I'm going to copy it and paste like that, and we got it in one column. You don't need to do that, but I like to do it. Okay, so let's go back here. We want to know the point estimate of the population mean. We cannot know the population mean, mu, but we can estimate the population mean, mu. We estimate the population mean, mu, with the sample mean known as x bar. So equal average. This function is the point estimator of the population mean. So we have the point estimator, which sums these 5 numbers and divides by 5. That right there is the point estimator. When I divide, or when I hit enter, the numbers in cells A1 to A5 are going to be added and then divided by 5. So the point estimate of the population mean is 73.6. Okay, and CengageNOW is calling for 5 decimals. So I'm going to add a bunch of decimal places here. Copy. I'm going to paste that into CengageNOW. Now I want the point estimate of the population variance. I want to know what the population variance is. The population variance is the sigma squared. We can't know the population variance, but we can estimate the population variance. The point estimator for the population variance is the sample variance. In Excel, you use var.s. .s is for a sample. .p is for the population. So the point estimator of the variance of the population is this command. When I hit enter, I get the point estimate of the population variance, which is 7.8. CengageNOW is calling for 5 decimal places. Next, I got to get the critical value of a 95% confidence interval for the population variance. This down here is the expression or the inequality that is used to build a 95% confidence interval for the population variance. Well, the confidence level, 1 minus alpha, is 0.95. That means significance, alpha, is 0.05. Because there's 2 numbers, 1, 2, of any confidence interval, we have to divide the significance level by 2, 0.025. Notice I replaced the subscript down here, alpha divided by 2, with 0.025. And then 1 minus alpha divided by 2 is 0.975. So I'm going to replace this value here, this subscript, with 0.975. Now the sample size was 5. I had 5 observations, correct? 1, 2, 3, 4, 5. I had 5 observations in the sample. 5 minus 1 is the degrees of freedom. So I have to go to row 4 of the chi-square table. In row 4 of the chi-square table, under 0.025, I get the critical value from the chi-square table for the lower number in the confidence interval. And I replace the chi-square subscript 0.025 with 11.143. Again, I go to row 4, which corresponds to degrees of freedom, and column 0.975 to get the other critical value. So I'm in column 0.975, row 4, because I had 5 observations and 5 minus 1 is 4. So 0.484 is the value I'm going to put in the denominator of the upper value of the confidence interval. So I'm going to copy the upper critical value, and I'm going to paste it here. I'm also going to paste it in my spreadsheet. Then I'm going to grab the lower critical value in column 0.975 in row 4 and paste it here and in the Excel spreadsheet. Okay, so in part C, the critical values of a 95% confidence interval for the population variance are 0.484 to 11.143, and they're both the 3 decimal places. Now I'm going to have to actually go and calculate the confidence interval for the population variance. I'm going to do that in Excel. Before I go to Excel, I'm going to grab this equation using the snipping tool, or this inequality. I'm going to paste it. Right here to guide me. Okay, so the lower limit of the confidence interval and the upper limit of the confidence interval I'm going to put those values right here. So what do I have to do for the lower limit of the confidence interval? I have to take the n minus 1, 5 minus 1. I got to multiply that by the sample variance. And that right there is my sample variance, right? Remember I did that? And then I can divide by the upper critical value from the chi-square table. So you kind of crisscross. This number goes down here. This number goes up here. When I divide a number, when I divide a number by something that's big, I get something small. When I divide something by something small, I get something big, which is why you crisscross. Okay. To get the upper limit of the confidence interval, I take the 5 minus 1, my degrees of freedom, multiply that by the sample variance, and then divide by the lower critical value. So when you divide by the lower critical value, you get a big number. When you divide by the upper critical value, you get a small number. And then CengageNOW wants these numbers to 3 decimals. So I'm going to reduce these numbers to 3 decimals. Okay, I'm going to copy this one and paste it in CengageNOW. And I'm going to copy this number, paste it in CengageNOW. Okay. Now the next thing I want to do is I want to get the 95% confidence interval for the population standard deviation. We prefer to talk about things in terms of standard deviation. We have heights here, and the variance, so those are in inches, right? We have inches. The variance here, this is actually in the mean is in inches, and the variance is in inches squared. So we don't really want to talk about the variance. When we talk about the dispersion of the data set, we really want to talk about the standard deviation. So in order to get the confidence interval for the standard deviation, all we do is we take the square root of the lower limit of the confidence interval for the population variance, and then do the same thing with the upper limit of the confidence interval for the population variance. So this is the confidence interval, 95% confidence interval for the population variance. This is the confidence interval for the population standard deviation. Now I'm going to copy each one of these individually into CengageNOW. So we have everything done to this point. I'm going to go ahead and check my work, and I should get all green check marks. I do. In part F, the confidence level, 95%, is the probability that the interval above contains the population variance. That is not accurate. The probability that the above interval contains the population variance is either 1 or it is 0, because the population variance is either in this interval or it's not in the interval. If it's not in the interval, the probability is 0. If the population variance is in that interval, it is 1. Because we are not Greek gods, we don't know the value of the population variance. We have to estimate it. We're mortals. We have to estimate it. So that 95% means what? Well, confidence level 95% is the percent of confidence intervals constructed that will contain the population variance. So if we replicated this procedure 1,000 times, so we have 1,000 samples, and all those samples are of size 5, 950, or 95%, 950 of the 1,000 intervals constructed will contain the true population variance. 50 of them, or 5%, will not contain the true population variance. Now, in reality, we're not going to do this 1,000 times. We may do this once, because sampling is very costly and expensive. So we're going to click the second option, and then I'm going to check my work. And it looks like I got all of the problems right. In question 2, we're going to do a hypothesis test for a single variance. Now, we're going to assume the standard deviation of female weekly earnings is a constant $61. And it's been like that because that's been like that for decades. It's been fairly consistent for, decades. And what you're interested in to find out is whether there's a difference in the variance of female, which we're holding constant at $61. We're assuming we know the sigma squared for females is $61. We want to know if the male variance equals that $61. So to test this, you sample 28 males, which provides a sample standard deviation of 63.2. Now, notice that the null hypothesis here and the alternative hypothesis begin with sigma squared. Well, the sample standard deviation is 63.2. Up here, we're assuming the population standard deviation is $61. So when we choose the option for the null and the alternative hypothesis, we have to square the $61. So anywhere down here where you see 61, you do not choose those. And 61 squared is 3721. So we're going to be choosing one of these that ends in 3721. Now if you come back up here, again remember the variance of female is some known, maybe the Greek gods have shined down upon us from above and have said sigma squared for females is $61. Or sigma for females is $61. So, and we want to know if there's a difference between that variance of 61 squared and the male variance. So that's that right there, the difference. That suggests that this is a two-tailed test. So for the alternative hypothesis, we're going to choose not equal to 3721. Again, 3721 is 61 squared. Okay, so this right here is the alternative hypothesis. What's the opposite of that? Equal to. So for the null hypothesis, we're going to pick equal to 61 squared. Now, with alpha equal to 0.02, we want to determine the critical values of this test. So alpha divided by 2 is the significance. So I'm going to copy that. Also note that this is a two-tailed test. Not equal to is the same thing as less than or greater than. So this is a two-tailed test. We have to divide the alpha by 2. So significance. Actually, I'm going to write alpha equal to so significance level is equal to 0.02. Alpha divided by 2, because it's a two-tailed test, we have to divide the alpha by 2. The alpha divided by 2 is 0.01. Okay, now we need to copy some other stuff into Excel. The sample size is 28 males, and that yielded a standard deviation of 63.2. That standard deviation is the sample standard deviation. So my n here is equal to 28. The degrees of freedom is 27. The sample standard deviation was 63.2. The sample variance is the square of the standard deviation. In part B, we have to determine what the critical values are. Now remember, this is a two-tailed test. So, if this is a two-tailed test, enter the value of the lower critical value in the left answer blank and enter the upper critical value in the right answer blank. The critical values are found in the row corresponding to the degrees of freedom of the chi-square table. Now, because my chi-square table is more intuitive, we're going to use it instead of the book's chi-square table. And the reason my chi-square table is more intuitive is because if the two-tailed null hypothesis is true, then sigma squared is going to be equal to this value. Because the sample variance is going to hover near the true population variance, sigma squared. We expect this s squared divided by this number here, we expect that ratio to be close to 1. So a number that is close to 1 times n minus 1 is going to be close to n minus 1. So if a two-tailed null hypothesis is true, chi-square stat should be around n minus 1. So now we're going to open up my chi-square table. And you open it, the columns are color coordinated. Okay. So I had the degrees of freedom down the middle too. Why do I do that? Because the degrees of freedom is the center, or is associated with the hump of the distribution, the chi-square distribution. These values over here are all lower critical values. These values are all lower or smaller than the degrees of freedom. So these values over on this side of my table are lower critical values. The values up here are upper critical values. So if my significance level is 0.02 and it's a two-tailed test, I divide the 0.02 by 2, I get 0.01. So I start in this column and I go down until I get to the degrees of freedom, or degrees of freedom 27. So my upper critical value is 46.963, and I go down until I get to the same color column. So my lower critical value is 12.879. My upper critical value is 46.963. I'm going to go ahead and copy those values, and I'm going to paste in my Excel worksheet for this problem. So this right here is my lower critical value, and this is my upper critical value. Go back to CengageNOW. I have this value and I got this value, and both have to be in 3 decimals. So let me change it to 3 decimals. Highlight them and then shrink to 3 decimals. I'm going to copy the first one and paste that into CengageNOW. Then I'm going to copy the second one and paste that into CengageNOW. In part C, we have to compute the test statistic to 4 decimal places. So I'm going to open Excel back up. Notice the test statistic is the degrees of freedom times the sample variance divided by the hypothesized value. Remember that sample variance is the square of the sample standard deviation, and the hypothesized variance here is the square of the assumed value of the female standard deviation, 61. So, moving on, the test statistic, I'll call it test stat. It equals the degrees of freedom, in this case 27, times the sample variance for males, and then we divide that by the hypothesized male variance, which equals, in this case, the pretty steady female variance over the last few decades. So the test statistic is 28.98266. Reduce it to 4 decimals, and we paste it into CengageNOW. Now I'm going to go ahead and double check my work, see if everything so far is correct. It should be, and it is. So, is my test statistic in between the critical values? If it is in between the critical values, then the difference between the male variance and its hypothesized value is insignificant, and that is the case here. So we have evidence in support of the null. And for that reason, the null cannot be rejected. And then check my work, and we should have all the problems done correctly. And we do. In question 3, we perform another hypothesis test for the variance. In this one, we want to determine whether the standard deviation is less than 10 millimeters. So standard deviation must be less than 10 millimeters. Because we're testing variances and we're talking about a standard deviation here, that 10 millimeters has to be squared, and 10 times 10 is 100. So this right here says the alternative hypothesis is the variance less than 100. So the variance less than 100. So again, the alternative hypothesis here says the variance is less than 100. If that is the alternative, then the null must be greater than or equal to 100. Next, we need to determine the critical values. This is a lower tail test, and down here in B, if this is a lower tail test, you want to put NA in the right answer blank. The significance level is 0.05. Because it is a lower critical value or lower tail test, we don't divide it by 2. So I'm going to copy the significance level and paste it into Excel. Now we don't divide by 2. We divide by 1 because it's a one-tailed test. The sample size, each sample contains 30 randomly chosen pistons. So the degrees of freedom is 29. The sample variance, the sample standard deviation is 10.76. The sample variance is the square of that, and the hypothesized value from the problem was 100, or 10 squared. The standard deviation for the diameter of the pistons has to be less than 10. So that means the variance has to be less than 100. To get the lower, now remember we don't need the upper critical value because it's a lower tail test. So the upper value is not applicable. To get the lower critical value, we need to be in row 29 of the chi-square table. To get the lower critical value, we start at 0.05, the significance level. We go down until we get to row 29. We had 30 observations in our data. 30 minus 1 is 29. 42.557 is the upper critical value. 17.708 is the lower critical value. We paste that lower critical value into CengageNOW. In part C, we need to calculate the test statistic. To do this, I'm going to go ahead and put that lower critical value here too. To do that, we take the degrees of freedom and we multiply by the sample variance and we divide by the hypothesized variance. So the test statistic is 33.5755. I'm going to copy that and paste that into CengageNOW. So remember, this is a lower tailed test. In order to say that the alternative is true, the test statistic has to be less than the critical value. That is not the case. So at 5% significance, the null hypothesis cannot be rejected. So, what do we conclude about the firm? Your firm should not ship the 1,000 piston batch to Quinnifi Corporation because we are not meeting the less than 10 millimeter standard deviation requirement. If we ship the batch to Quinnifi, then we're shipping them pistons where the variance of those pistons is too great. I'm going to check my work, and we should get all the questions right. We get them all right. In problem 4, we have another test of a single variance. Only this time, we want the standard deviation to be equal to 1.1 minutes or less. So that right there, that highlighted phrase, is the null hypothesis. Now, the null hypothesis, instead of stating the sample or the population standard deviation, it is making a statement regarding the population variance. So we have to square the 1.1. And 1.1 is 1.21. So we go down here until we see less than or equal to 1.21. The alternative hypothesis is the opposite. So we're going to look for greater than 1.21. So this is an upper tailed test. Because it's an upper tailed test, we're going to put in A, the lower box. And we need to put the upper critical value of the test in this box. The significance level is 0.01. And the sample size is 30. Again, it's a one-tailed test, so we divide the alpha by 1. The sample size is 30. The degrees of freedom is 30 minus 1, 29. The sample standard deviation was 1.15. So the sample variance is the square of that. The hypothesized value is 1.21. We don't need the lower critical value. We need the upper critical value. Again, the upper critical value is in row 29 in column 0.01. So we're going to start in column 0.01 and go down until we get to row 29. So the upper critical value is 49.588. So I'm going to paste that right into here. And I'll go ahead and put that in my Excel spreadsheet too. The next thing on the docket is to calculate the test statistic. To calculate the test statistic, we take the degrees of freedom, multiply that by the sample variance, and divide that by the hypothesized variance. So our test statistic is 31.6963. I'm going to copy that into CengageNOW. So let's look at this. If this test statistic is greater than the upper critical value, we have evidence in support of the alternative hypothesis. That's not the case here. So our evidence supports the null. So the null cannot be rejected. Let me just double check my work here, and we should get everything but the last one correct. And we have. Because monthly performance bonuses are based on having standard deviation of 1.1 minutes or less, and that statement could not be rejected, employees at the call center will get monthly performance bonuses. And then I'm going to go ahead and check my work, and we should have everything correct, and we do. In question 5, you want to determine if Quinfinity Corporation stock is as volatile as TMI International stock. To do this, you collect a random sample of prices for both stocks. We have 41 random Quinfinity stock prices. The standard deviation was 5.78. Remember, we have to square that. We have 33 random TMI stock prices, and that standard deviation was 2.53, and we have to square that. If the Quinfinity stock is as volatile as TMI's, then the variances on these two time series should be equal. So the null hypothesis here is the variances are equal to each other. The alternative hypothesis is the variances are not equal to each other. Because the alternative hypothesis suggests that this is a two-tailed test, then we have to enter the upper critical value in this right answer blank and unnecessary in the left answer blank. And the reason for that is because for an F test, population 1 is determined by when the two sample variances are compared. Population 1 is always corresponds to the larger sample standard deviation. Since the largest sample standard deviation is 5.78, then that corresponds to Quinfinity stock price. The sample variance, this squared, for Quinfinity stock price will be put in the numerator of the F statistic. And the square of this will be put in the denominator of the F statistic. So now we need to find the upper critical value of this test. So I'm going to copy this stuff and paste it into Excel. The Upstat is the ratio of two sample variances, and it is defined to be, the ratio of the bigger sample variance divided by the smaller sample variance. So population 1 here is going to have a sample variance of 5.78 because it's bigger than the sample variance of the TMI stock price. The 41 stocks were used to compute the sample variance, or sample standard deviation 5.78. The 33 TMI stocks were used to compute the standard deviation of the TMI stock price. The degrees of freedom for population 1 is 41 minus 1. The degrees of freedom for population 2 is 33 minus 1. The sample variance is the square of the standard deviation. So we'll repeat that again. Now, this 33.4084 is larger than that sample variance. This value goes in the numerator of the F statistic, which means the 40 here is the numerator degrees of freedom. So the denominator degrees of freedom is 32 because this sample variance goes in the denominator of the F statistic. The significance level is 2%, and notice it's a two-tailed test, so we have to divide the alpha by 2. To get the upper critical value of the test, we have to go to row 0.01 and 32. Here's the F table. Row 32. There is no row 32. Suppose it was row 30. If there is no row, maybe we'll go to the closest one, say 30. Our alpha divided by 2 is 0.01. We would go over here until we got to column 40, right? So our critical value would be about 2.3. I don't want to be close, I want to be exact. So if you go to my website, my teaching website, and you click on F distribution calculator, 40 numerator degrees of freedom and 32 denominator degrees of freedom. This area in the upper tail is 0.01. So my F critical value is 2.523. And we only need 2 decimals, so I'm going to lop off the 3 and the 2. There is a lower critical value, but because we define Fstat as the ratio of the big variance divided by the small variance, Fstat can't be less than 1. So there's no point in getting this lower critical value. Now the Fstat is pretty simple. It's just the ratio of the big variance divided by the small variance. And I'm going to copy that and I'm going to paste that into CengageNOW right here. We only need 3 decimal places, so I'm going to chop off the 3. Now, going back up to part B, lower tail F tests are not performed because the population with the largest sample variance is placed in the numerator of the test statistic. It is unnecessary to find a lower critical value for two-tail F test because the test statistic is by definition larger than 1. Okay, so what have we got here so far? The test statistic is greater than 2.25. So the test statistic is not in between our critical values. And because it's not in between our critical values, the difference between the two variances is not insignificant. In other words, there's a significant difference in the two variances, which means we're going to reject the null. The null can be rejected at 2% significance. I'm going to check my work to make sure everything's good to go. And we got all the answers that we've answered correct. So, what is the data telling us? The data is telling us that Quinn Infinity has a larger variance in its stock price. So there's more ups and downs in Quinn Infinity stock price than in the TMI stock price. So if there's more ups and downs in Quinn Infinity stock price, then its stock's price is more volatile than TMI stock. And I'll double check my answers. And we should have them all correct. And we do. In question 6, we want to find out if the NASDAQ is more volatile than the NYSE. So we want to know if the variance for the NASDAQ is greater than the variance for the NYSE. We have 31 NASDAQ daily closes and 46 random New York Stock Exchange daily closes. The NASDAQ standard deviation is 9.19 and the NYSE's is 5.51. I've copied the sample sizes and the sample standard deviations from the CengageNOW problem into my Excel spreadsheet. The larger sample standard deviation is 9.19. The larger sample variance is 84.4561. I found that by squaring the sample standard deviation. The smaller sample variance is found by squaring the smaller sample standard deviation. The Upstat, remember, is the ratio of the bigger sample variance divided by the smaller sample variance. So the numerator degrees of freedom is 30. The denominator degrees of freedom is 45. This goes in the numerator of the Upstat. That goes in the denominator of the Upstat. Hence, this is the numerator degrees of freedom, and this is the denominator degrees of freedom. The alpha level for the problem, the significance level for the problem, is 1%. In part B, we want to determine the critical values. But before we do that, we have to determine what our hypotheses are. So remember, NASDAQ, we want to know if NASDAQ is more volatile than the NYSE. So we want to know, that right there is indicating, that phrase there is the alternative hypothesis. So the variance for NASDAQ is greater than the variance for New York Stock Exchange. So the null hypothesis is less than or equal to. This is an upper tail test. So because it's an upper tail test, we're going to put NA in the left answer blank. And we need to get the upper critical value for this upper tail test in the right answer blank. So it's a one-tailed test, so we divide alpha by 1. We're in row 0.01 and 45 of the F table. So let's find the F table. Okay. 0.01 and 45. That's the row we're in. We don't have a row 45. So instead of doing that, we're going to go to the F distribution calculator on my website. So denominator degrees of freedom is 45. 0.01 is the alpha level, and then the numerator degrees of freedom is 30. So 30, 45, and 0.01. So the F critical value is 2.14. And notice it is bigger than 1. The upper F critical values are always bigger than 1 because the hump of an F distribution is close to 1. All of the lower critical values for the F table would be less than 1 because, again, the hump is near 1. And a ratio of equal variances would have an F statistic that is near 1. The lower tail F tests are not performed because the population with the largest sample variance is placed in the numerator of the test statistic. It is unnecessary to find a lower critical value for the two-tailed F test because the test statistic is by definition larger than 1. I got to reiterate that point over and over and over. Going back to the Excel spreadsheet, the F statistic is the ratio of the bigger variance and the smaller variance. So here it is 2.7818. Copy that into CengageNOW. We only need 2 decimal places, so 1/8, that becomes 2. Our test statistic is bigger than the upper critical value, which means we can accept the alternative hypothesis and reject the null. So the null can be rejected. So what does that say? We can actually say the NASDAQ is more volatile because we can reject the null outright. NASDAQ is more volatile than New York Stock Exchange. Check my work and we should get 100%. And we do.